Hi everyone. This is lecture 30 on the regulation of urine concentration and volume. So in this lecture we're going to go into much more detail of the different processes that occur to provide the final urine output. And your textbook does a fairly good job at separating the different processes, but you got to keep in mind that they're all kind of occurring at this simultaneously. So in this lecture, we're going to talk about the regulation of urine concentration, and that's going to be the big component of the lecture. And in order to do so, we're going to have to learn several concepts, such as the countercurrent mechanism, which includes the countercurrent multiplier, the countercurrent exchanger. Okay, and then we're going to describe the final urine composition and clearance. We'll talk about the process of micturition or urination. And just briefly, acid-base homeostasis. I think I just left one slide remaining from last year's lecture. Okay. So, in order to talk about the urine concentration volume, we have to keep in mind that there are two types of water absorption reabsorption is going to be occurring. There's going to be obligatory water reabsorption as well as facultative water reabsorption. 85% of the water absorption is obligatory, meaning that's required. It will happen, regardless of the water and concentrations of the solids. However, there's 15% of water absorption is facultative, meaning that this could increase or decrease among this 15%. And so this is what the facultative water absorption is what determines whether the urine is dilute or concentrated. Okay, so let's go where we left off. The filtrate is entering and leaving the renal corpuscle is isoosmotic to plasma at about 300 milliosmoles. Okay, if you're not familiar with this term, milliosmoles, this is just the means of quantifying the solute concentration. Okay, so we're saying here that the filtrate and the blood are the same concentration at 300 milliosmoles. Okay, now two important concepts we're going to talk about, and you have to keep these straight in order to make it make sense. If you forget this, then it gets confusing. The thin descending limb of the loop of Henle is permeable to water, but not solutes. Okay, only water. The ascending limb is impermeable to water. Okay. So if you remember to keep these two concepts straight as we go along. Okay, so in these boxes here I show this fact that the descending limb is permeable to water, not solids, and here showing the ascending limb is permeable to solids but not to water. And here we see that the filtrate that exits the blood from the glomerulus enters the nephron is isoosmotic at 300 milliosmoles. So 300 milliosmoles here and 3 milliosmoles here. So at the very beginning, it's the same concentration. Let's begin with the filtrate of the descending limb. The descending limb is permeable to water but not solutes. Okay, that's one of the concepts I told you to remember. And because it's permeable to water, the solids will be concentrated as it travels down the loop. And by the time it gets to the bottom of the loop, it becomes to 900 milliosmoles. So it's become more concentrated as we went down the descending limb. Okay? And this is due to the reabsorption of water. So we see as water is removed, it goes from 300 to 350 to 550, 70 to 900 at the turn of the loop of Henle. So we have an increase in solute concentration as we go down the descending limb. Now, the ascending limb, sodium and other ions are pumped out as it enters the ascending limb. Okay, because these were concentrated in the loop, and so now at the ascending limb they're going to be pumped out. But remember, the ascending limb is now impermeable to water. Okay, and as a result, as the pumping of the solutes occur as we go up the ascending limb, it becomes less concentrated, and it becomes about 100 milliosmoles at the ascending limb, at the end of the ascending limb and distal tubule. Okay, so from here at 900, we see that sodium chloride is being pumped out, and as a result, the solute concentration decreases to 150 as it leaves the ascending limb. Okay. Okay, vacuum water reabsorption begins in the late distal tubule and collecting system. Okay, and this is when there's less. We find that there's less water reabsorbed without ADH. Okay, so without antidiuretic hormone, less water is reabsorbed, and as a result, you're going to have more water being excreted, and it's going to be more dilute. Okay, especially when the solute concentration is very low. You're going to produce a dilute urine. Now let's look back at the sodium chloride reabsorption. This continues in the distal tubule and collecting system. And as a result, solutes decrease while the amount of water remains the same. Okay, if that occurs, then it's going to become more dilute. Okay, so if the amount of water is in excess, it may be as low as 50 milliosmoles. So here, at the descending tubule and the collecting ducts, we see sodium chloride being reabsorbed. Okay, the water stays the same. It's going to become more dilute. So we can feasibly produce a urine that's 50 milliosmoles, or very dilute. Okay. So normally, so formation of a dilute urine, normally it's about 300 milliosmoles, we said. If there's excess water, a larger urine volume is produced, maybe almost 2 liters per day. Okay. However, the urine volume is affected by fluid intake, your general health, diet, and blood pressure, so the volume can vary from individual to individual. Okay. Okay. So this is just showing the same figure again. Okay. Okay. Now, because we have what's called the medullary osmotic gradient, we have the ability to produce a very concentrated urine as well, up to 1200 milliosmoles. Okay, so that's much more concentrated. And this is due to the medullary osmotic gradient. Okay, this results from the fact of water reabsorption in the late distal tubule collecting system. Okay, but it only occurs if the interstitial fluid is more concentrated than the filtrate. Okay, so remember the interstitial fluid in the renal cortex is about 300 milliosmoles. The filtrate entering the late distal tubule and cortical collecting duct has an osmolarity of 100 milliosmoles. So there's a tiny gradient for water reabsorption. So here, interstitial fluid is about 300 milliosmoles. Okay, and in the going into the distal tubule, it's about 100 milliosmoles. So there is a slight gradient for water to move out from less concentrated to more concentrated. Okay. Now, how can we produce a concentrated urine? Well, the kidney is able to produce what's called a countercurrent mechanism. Okay, and that small gradient we had from 300 to 100 disappears when the filtrate enters the medullary collecting duct. So we must have to find another way of making a gradient for water to be reabsorbed. Okay. So when the filtrate enters the cortical collecting duct in the renal medulla, there's no more osmotic gradient between the filtrate and the interstitial fluid. So here it's 300 here in the interstitial fluid and 300 here in the collecting duct. So there's no driving force anymore for water. So what can it do? What can it do? And so this is where the countercurrent mechanism is used to produce a concentrated urine. Okay, and what it does, it creates a concentration gradient, so osmosis will occur. Okay, without a concentration gradient, osmosis will not occur within the renal medulla. So how does it make this medullary osmotic gradient? Well, one, the blood in the vasa recta here loses sodium chloride and gains water as it ascends toward the renal cortex. Okay, actually I'm going out in the wrong order here. Let's start with 1 here. Okay, because here's the vasa recta. Okay, and the blood in the vasa recta gains sodium chloride and loses water as it descends into the renal medulla. Because remember, it's getting more concentrated as we go down into the deeper medulla, and this is due to the fact that sodium chloride is moving from the tubule to the vasa recta, and as it does this, this is going to increase the concentration, solid concentration of the peritubular of the vasa recta down here, and so that makes it very high down here. And then as the vasa recta ascends here, it's going to lose sodium chloride, okay, because it's now so concentrated, and it will gain water as it ascends toward the renal cortex. And this preserves the gradient in the renal medulla, because here, as water is reabsorbed and sodium chloride is pumped out, this decreases the solute concentration here in the vasa recta. Okay. So because of these actions, the concentration in the vasa recta will increase as we go toward the loop, and then decrease as it ascends back up. Okay. So this concentration gradient is created by the countercurrent mechanism. Okay. And there are 3 factors that will contribute to the countercurrent mechanism. One is the countercurrent multiplier. The second is the recycling of urea in the medulla. And the third is the vasa recta countercurrent exchanger. Now, we're going to talk each one individually, but all 3 contribute to this medullary osmotic gradient for the countercurrent mechanism. Okay? Because it would be really confusing if we try to talk about them all at the same time. Let's begin with the countercurrent multiplier. Okay? This involves the long loops of juxtamedullary nephrons. Remember, there are 2 types of nephrons. The cortical nephrons, which are primarily in the cortex, have shorter loop of Henle's that dip just a little bit into the medulla. And then there's also the juxtamedullary nephrons, whose renal corpuscles are closer to the medullary cortex boundary, but have very long loops of Henle, and they're surrounded by the vasa recta. Okay, and this contributes to the medullary osmotic gradient. Okay, the term countercurrent refers that the filtrate of the 2 limbs flow in opposite directions. We're going to see that the filtrate in the tubule is moving in the opposite direction of the vasa recta, the blood in the vasa recta, and this is a very common practice in nature, because it helps you to amplify the system. Okay, and this is where the multiplier comes into play. Multiplier refers to the effective increase from processes that use ATP. So we're going to talk about ATP processes to help get this done. Okay, so here is showing the countercurrent multiplier. Okay, because the 2 loops, one loop is going one way and the other loop is going the other way. Okay. There are 4 steps for the countercurrent multiplier, and we'll talk about each one. The first step involves sodium chloride being actively transported by a sodium-potassium chloride symporter. So for every sodium-potassium, 2 chlorides are pumped across. The second step is the concentrated interstitial fluid creates an osmotic gradient, and that's what we want so that water can move, so we can have a concentrated urine. As water leaves, sodium chloride remains in a thin descending limb, because remember, that was permeable to water, but not to salt. Finally, the highest sodium chloride concentration of the filtrate reaches the thick ascending limb that allows sodium chloride reabsorption to continue. So let's talk about each of these 4 steps. The first step involves sodium chloride actively transported by the sodium-potassium chloride symporters. Okay, movement from the filtrate in a thick ascending limb loop to the interstitial fluid, and this is going to increase the osmolarity of the interstitial fluid. Okay, so here we see that sodium chloride is being pumped across from the ascending limb, and that's going to increase the concentration of the interstitial fluid in the medulla, renal medulla. Okay. As a result, it's got this higher solute concentration is going to pull water from the filtrate from the descending limb into the interstitial fluid. Okay, so in the descending limb, because of the increase in solids in the interstitial fluid, water is going to be actively osmotically moved out from the descending limb by osmosis. Finally, as water leaves the sodium chloride remains in the thin descending limb. Okay, remember the thin descending limb is permeable to water, but not to solids. So the filtrate becomes more concentrated as it reaches bottom of the nephron loop. Okay. So because of the pumping of the sodium chloride from the ascending limb, water is going to move osmotically out of the descending limb. This is going to concentrate the salts in the descending limb as we increase down toward the turn of the loop of Henle. It's going to increase. Okay. Finally, the high sodium chloride of the filtrate reaches the thick ascending limb again and allows sodium chloride to reabsorption to continue. These symporters begin pumping sodium chloride into the interstitial fluid as we return to step 1. Okay, so as the high solute concentration from the descending limb turns a corner, in the ascending limb it's going to be pumped out. Okay, and then the whole thing starts over again. From the descending limb, water will follow the solutes to be osmotically move out, concentrating the solutes so that in the ascending limb, the solids will be pumped out. And this is the countercurrent multiplier. It's the movement of solutes, the differential movement of solids from the ascending limb from the descending limb, so that water will move from the descending limb to set it up the higher concentration gradient for sodium chloride to be pumped again. So as filtrate moves up the ascending limb, sodium chloride is pumped out, decreasing sodium chloride in the filtrate. Okay. So we have these alternating exchanges of sodium chloride being pumped out in the ascending limb and water following passively from the descending limb. Okay. So that's one process. The second process is urea cycling. Again, that process was to increase the solute concentration in the medulla, renal medulla. Okay. Another process that will do this, similar action is urea recycling. Okay. The medullary collecting system is permeable to urea. Okay. So as urea becomes concentrated, as water is reabsorbed from the filtrate, urea becomes more concentrated as water is reabsorbed from the filtrate. In the medullary collecting and papillary ducts, urea diffuses out of the filtrate and into the interstitial fluid. And some urea enters the descending limb of the nephron to rejoin the filtrate. Okay? So we hear in the collecting ducts here, we see urea is permeable and can diffuse out. Okay? And this urea will move into the descending limb. Okay, but by diffusion. Okay, and this is also going to help maintain the medullary concentration gradient as we go down deep in the medulla, and then as we move up the descending limb, it will get decreased. Okay. Another process that occurs is a vasorectite and a countercurrent exchanger. Okay. In this case, the countercurrent exchanger is due to the opposite movement of the filtrate and the blood flow to help maintain a steep osmotic gradient. So here we see the vasa recta moving downward, opposite to the ascending limb, and the vasa recta moving upward when the descending limb is moving the opposite direction. So here, countercurrent exchanger is comparing the blood flow versus the flow of the filtrate. Okay, so the blood of the vasa recta is going to gain sodium chloride and lose water as it descends into the renal medulla. Okay, so it's going to gain sodium chloride. It's going to increase the solute concentration as we go down here, and also water is going to follow, concentrating it to 1200 down here. As we go to the ascending limb, the vasa recta loses sodium chloride by diffusion and gains water by osmosis as it goes towards the renal cortex. And this is also going to preserve the medullary concentration gradient as it moves upward. It's going to get less and less as sodium chloride is pumped out and water is being reabsorbed. Okay. So blood descending into the medulla is hypoosmotic to the interstitial fluid, about 300 milliosmoles. Water leaves the blood and enters the interstitial fluid by osmosis. Sodium chloride diffuses from the interstitial fluid to blood, increasing to 1200 milliosmoles in the deep medulla. Okay, so this is what we just said. I kind of got ahead of myself here. Secondly, the gradient reverses as the vasa recta ascends the medulla. Blood is hyperosmotic to the interstitial fluid. Sodium chloride diffuses out of the blood and into interstitial fluid. Water moves by osmosis from interstitial fluid into blood. So here, as we move up, sodium chloride will diffuse out, and water is going to be reabsorbed as we move upward, and it's going to start diluting the vasa recta as we move up. So we have preserved this medullary gradient because of these three processes, where as we go deeper into the medulla, it becomes more concentrated. Sodium chloride removed from the interstitial fluid in the descending limb of the vasa recta was exchanged into the interstitial fluid by blood in the ascending limb of the vasa recta. Okay, osmolar is back to 300 milliosmoles when it exits the medulla. So what we mean by exchanger is the sodium chloride that's been pumped out from here, from the vasa recta as it goes down, gets put back when it goes back up. It gets diffuses back out, and so this sodium chloride is being kind of recycled here, where it's pumped out. I mean, sodium chloride moves into the vasa recta here, where it moves out in the as it goes up. Okay, so the question is, how does the countercurrent mechanism concentrate urine now? We have this medullary concentration gradient formed by these three processes. Okay, it's all set up, but remember, normally the collecting duct is not going to be too permeable to water, but it will be actively reabsorbed from the collecting ducts when ADH is present and when a concentration gradient is there to drive osmosis. Okay, so when we have the second one ready, all we need is the first one. And so the medullary osmotic gradient must be maintained just in case we need to conserve water. And so, to recap, the medullary osmotic gradient that's produced is maintained by the countercurrent multiplier, this continuous solute reabsorption and urea recycling, and the countercurrent exchanger. So these three processes is what's going to maintain the medullary osmotic gradient if we need to make a concentrated urine. Okay, so let's take a look at this. The filtrate enters the renal medulla, has the same concentration as the interstitial fluid, and as a result, there's no gradient to drive water reabsorption. Okay, so here's a late distal tubule in the collecting duct, and in the renal medulla, it's also 300 milliosmoles. So there's no driving force for concentrating the filtrate. However, when antidiuretic hormone is present, the medullary interstitial fluid creates a gradient for water reabsorption from the filtrate of the medullary collecting duct. And so water passes through these aquaporin channels. The water is reabsorbed until the filtrate and interstitial fluid are isoosmotic. So in the presence of ADH, we have these aquaporin channels that, because of this increase in concentration gradient in the interstitial fluid, water is going to be reabsorbed all along the length as we go deeper into the medulla. And that was the whole point of making that medullary concentration gradient, so that if ADH is present, we can conserve water and reabsorb it if needed to. Water reabsorption continues because the interstitial fluid becomes progressively more concentrated deeper into the renal medulla. Okay, remember the renal medulla is getting more concentrated. So as we go down toward the medulla, water is going to be reabsorbed more and more. And this is going to concentrate the filth of the urine. So we can produce a concentrated urine, 1200 milliosmoles. And so that's about the highest we can obtain. Okay. Of course, like the desert kangaroo rats, they have much longer loops of Henle, and so they can produce a much more concentrated urine than we can. Okay. And so it can only make a concentrated urine for us. It's only going to make a concentrated urine up to 1200 milliosmoles because we no longer have a gradient to drive the osmosis. Okay. But some animals have a much longer loop of Henle, and so they can make a much more concentrated urine. Okay, so let's look at the picture of renal physiology. And so here is of course, the whole nephron, the collecting duct, and we have the vasa recta, and this describes each of the events that occurs throughout the length of the renal tubule and collecting duct. Okay, so it's kind of intimidating at first, but if you break down these processes that are occurring simultaneously, and then think about them when they're all occurring at the same time, we see that the nephron is going to produce this increase in solute concentration in the interstitial fluid as we go deeper into the medulla, so that if we need to create a more concentrated urine, ADH can be secreted, and we can produce a more concentrated urine in the end. Okay. If ADH is not present, then we don't need to conserve water. However, that concentration gradient is still there just in case. Okay, so let's look at the urine composition now for a normal individual. And so here I have things that are present, things that are in trace amounts, and things that are absent. Let's start with the things that are absent. You shouldn't have blood, protein, you should not have white blood cells or glucose present in your urine. Okay. You might have trace amounts of bicarbonate, calcium, and magnesium. Things that are present include water, creatinine, sodium, ammonia, potassium, uric acid, chlorides, sulfates, urea, and of course hydrogen ions. Okay. Urinalysis is a quantitative analysis of the urine, and there are different qualifications we look at, like color, translucency, odor, pH, and specific gravity are a few. Color. It's yellow due to urochrome, which is a breakdown product of hemoglobin. Okay. Of course, the color can also be influenced by different foods, vitamins, drugs, dyes, and of course, blood will change its color as well. Normally, the urine should be translucent. Okay, a cloudy urine may indicate an infection or large amounts of protein. The odor, it should have a mild odor. It may be altered by disease states such as diabetes mellitus, where it might sound sweet smelling, infection, and in foods. pH. The urine should be about pH 6, but can range normally from 4.5 to 8. Finally, specific gravity. Specific gravity compares the amount of solids in a solution to the amount of deionized water. In deionized water, it's been normalized to 1.0. So anything higher than this has more solids. So urine should range between 0.001 and 0.035. So the urine is relatively not relatively dilute. Okay. Let's look at micturition. Okay. which is urination or voiding of the urine. Okay. So micturition is the discharge of urine from the urinary bladder. And it's acted by the micturition reflex, by the parasympathetic nervous system. So micturition is under parasympathetic control. And in this reflex, it's stimulated by stretching of the urinary bladder. In infants and young children, this involuntary reflex is primary stimulus to empty the bladder. Usually they feel it stretch and they get the sensation of urinating, and until they have control, that's what they'll do. Okay, so here the urine fills the bladder and stretches the wall. Okay. The stretch receptors send sensory afferent signals to the sacral spinal cord. Okay. So here they're sending signals to the sacral spinal cord. Okay. The parasympathetic afferent fibers stimulate the detrusor muscles to contract and internal urethral sphincters to relax. And this causes micturition. Okay. So from here, it's going back. Okay. To stimulate the detrusor muscle and relax the internal urethral sphincter. So as children mature, pathways develop between the parasympathetic neurons and the brain. And this allows for voluntary control over the external urethral sphincter. Okay. And so two additional steps simultaneously occur when the bladder is full. Okay. Interneurons in the spinal cord communicate to the micturition centers in the pons. So here we have the interneurons in the spinal cord communicate to the full bladder signal to the micturition centers in the pons. Okay, here. Okay. Now, if micturition is appropriate, the cerebral cortex allows the external urethral sphincter to relax, and then urine is voided. Okay. So here is it from the brain centers to the voluntary control of allowing the external urethral sphincter to relax, and the urine is voided. Okay. If micturition is not appropriate, the detrusor muscle relaxes and the internal and external sphincters remain closed. Okay. The urge to urinate passes and initiates again in about an hour. The cycle repeats until about 500 to 600 milliliters has been filled in the bladder, and at that point, voluntary control is lost. So you can't put it off forever. Now, I cut out most of this from the lecture to make it shorter, but one of the important functions of the urinary system is to regulate blood pH. So not only the kidneys, but the lungs determine the number of hydrogen ions and basic ions in the blood. One of the ways it does this is by secreting bicarbonate to act as a buffer. Okay, and so that kidneys maintain acid-base balance by controlling the bicarbonate in the blood. Having more bicarbonate will buffer more hydrogen ions, and of course less if there's less. Okay. Hydrogen ion secretion occurs in the distal tubule and collecting system. Okay, so we can remove a lot of hydrogen ions that way. The intercalated cells have primary active transporters that pump hydrogen ions into the filtrate. Okay, and so this is the end of this lecture, and this deals with many of the factors to regulate whether urine is going to be dilute or concentrated. Okay, thank you.